Hello everyone. My name is Jungjie Chen from the University of Electronic Science and Technology of China. It is my great pleasure to present our work on behalf of our team. My teammates Aoran Liu, Yushen Wang, and Junbo Zhang and I are very excited to share our ideas with you. As you can see from our slides, we have chosen to address question 2, how can we overcome unique propagation challenges, such as atmospheric absorption and scattering, at terahertz frequencies in wireless communication systems? This question forms the main theme of our presentation. Our presentation is organized into 4 parts: background, key challenges, proposed methods, and implementation. So without further ado, let us begin with the background. First is the background. As conventional low-frequency bands become increasingly crowded, research is shifting toward higher frequencies to meet growing demands. Lower frequencies offer limited bandwidth, which restricts both sensing accuracy and data transmission rates. By moving to higher frequencies such as the terahertz range, we can achieve substantially better sensing resolution and much higher potential data rates. However, higher frequencies also come with several drawbacks, such as more substantial path loss and penetration loss. Therefore, when we move into terahertz communication, the key problem we must solve is how to maintain sufficient coverage in different scenarios. So what are the main challenges of terahertz communication? There are typically 3 main challenges in terahertz wireless communication, namely high path loss, large-scale frequency selectivity, and severe blockage. First, high path loss. The higher the frequency, the greater the attenuation. At terahertz frequencies, attenuation is extremely high, potentially tens of dB more loss than at microwave or millimeter wave frequencies. Second, terahertz signals experience strong frequency-dependent propagation effects. Molecular absorption and other phenomena cause the channel response to vary greatly across the band, making the large-scale channel highly uneven. In other words, certain subbands within the terahertz spectrum may suffer high loss or attenuation peaks, while others are more benign. Third, severe blockage is the most critical challenge. Terahertz signals are easily blocked by obstacles. Signal strength can drop abruptly by tens of dB, even over 40 dB, from something as simple as a moving hand or arm. Moreover, the link becomes very fragile under dynamic conditions. When people or objects move around, the connection can be suddenly interrupted. This demonstrates how sensitive high-frequency links are to blockage. To mitigate the high path loss, one approach is to exploit the very small wavelength of terahertz signals. As the wavelength decreases, antennas can be made much smaller, allowing a large number of antenna elements to be packed into a compact array. Using these massive antenna arrays on the transmitter or receiver, we can form highly directional, high-gain beams, which help compensate for the severe free space path loss. For the frequency selectivity issue, we can adopt a macro-level solution that leverages the uneven attenuation across the terahertz band. The idea is to perform large-scale frequency allocation. We divide the terahertz band into multiple sub-bands. We then assign the most robust sub-bands to users that are far away, and assign the more sensitive sub-bands to users that are nearby. However, even with the above measures taken, the severe line-of-sight blockage problem remains a challenging issue, which is also the focus of our today's presentation. Next, we will introduce our ideas for overcoming the blockage challenge, illustrated by a few simple analogies. Let's think. When we face a problem, how to overcome it? Basically, there are 3 types of methods. First, direct effort. If we have enough strength or skill and make full use of them, we push the boulder ourselves. Focus, commit, and move it. Second, seek support. We ask for help. With teammates, mentors, or tools, we combine strengths and get over the obstacle. Third, smart detour. If a head-on push won't work, we change the path. We look for a new route, redesign the plan, and reach the goal another way. We have investigated solutions corresponding to each of these approaches in the context of terahertz communication. The direct approach is to fully reuse the SSB signals intrinsically defined in 5G-NR for beam training. Moreover, the wide bandwidth of terahertz signals is itself beneficial for sensing. Hence, SSB signals over terahertz band is our intrinsic strength. SSB signals enable the base stations not only to perform beam scanning, but also to detect blockages and track mobile terminal in real time. When a blockage is detected, the system triggers a handover process by instructing the nearest available base station to send an additional SSB burst for inter-cell handover. In addition, a resource allocation ratio can be introduced to balance the resources used for both sensing and communication. SSB signals can be reused to recover the channel matrix, to locate the blocks and users for handovers. Simulation results demonstrate that our approach significantly reduces misalignment in both highway and urban environments. By adjusting the resource allocation ratio, the system achieves even lower misalignment probabilities. These findings highlight the effectiveness of our sensing-aided method to mitigate severe blockage of terahertz networks. The next method is to seek support, and our support is from reconfigurable intelligent surfaces. RIS can create additional virtual line-of-sight links to bypass obstacles. The central challenge lies in a fundamental cost-coverage trade-off. Denser RIS deployment can provide more virtual loss paths, and hence better coverage performance, but it inevitably increases deployment cost. Conversely, sparser deployment reduces cost, but may significantly degrade coverage quality. Therefore, our proposed method aims to balance this trade-off by formulating and solving a multi-RIS deployment optimization problem, which I will introduce next. To solve this deployment optimization problem, we adopt a graph-based solution. Step 1 is to construct the loss graph based on the topology of the environment, where vertices represent candidate deployment cells and edges denote direct path or reflection paths. By assigning appropriate weights to the edges, we can evaluate the average coverage performance for any given deployment scheme. Step 2 is the optimization stage. For the resulting discrete deployment optimization, we can use a branch and bound algorithm to obtain an optimal solution at the cost of high complexity. Alternatively, we can seek more efficient suboptimal solutions. For example, we introduce a successive RIS removal method. This algorithm starts with all RIS deployed, then iteratively removes those with the least contribution, while ensuring that the coverage constraint is still satisfied. It offers a favorable balance between accuracy and efficiency. Here I present our simulation results. The left figure shows the trade-off curve between deployment cost, measured by the number of RIS deployed, and coverage performance, measured by the average RIS number required to establish a loss path to any location. As more RIS are deployed, the coverage improves. However, the improvement saturates after deploying a sufficient number of RIS. The right figure indicates that, if we incorporate B's deployment optimization, the trade-off can be further improved. The third approach is to find an alternative propagation path by taking advantage of advanced beam physics. Specifically, we explore using non-diffractive beams that can bend or self-heal around obstacles. Thanks to the very short wavelength and the resulting large near-field region at terahertz frequencies, large-scale antenna arrays have more flexibility in beam forming and can generate exotic beam patterns. We focus on two types of non-diffractive beams: airy beams, which exhibit a self-bending trajectory, and BSSEL beams, which have a self-healing property. Both beams can reform their shape after encountering an obstacle and do not diffract like conventional beams. For example, by properly generating an airy beam, the signal can bypass the obstacle to reach the blocked user position. An airy beam is a solution of Helmholtz equation where the beam travels along a curved path while maintaining its shape. In theory, if an antenna array launches a wave whose amplitude profile follows an airy function, the main lobe of the beam will curve as it propagates. In practice, generating an airy beam requires a carefully designed phase front. Using a metasurface or a phased antenna array, we can imprint the required phase variation across the aperture. For example, imagine that the antenna array is divided into many tiny radiating elements. We can design a beamforming vector such that the emission from each array element combines into a wavefront that is tangent to a predetermined curve. This leads to an efficient solution to generate a bending beam following different trajectories. Both simulation and experimental results for bending beam forming. In simulation, the airy beam propagated along the intended curved path and maintained its intensity profile over a longer distance than a normal diffracting beam. In our experimental test, we generated a 140 GHz airy-like beam, and observed that the beam indeed follows the preset trajectory and can go around an obstacle placed in its nominal straight-line path. These results confirm that non-diffractive beams are naturally more robust against small obstructions. In addition, we also conducted link-level experiments, which will be introduced later in the following part. Having explored these three approaches to mitigate blockage, we can compare their characteristics and appropriate application scenarios. Sensing-aided method is a proactive but more complex solution, as it involves the network coordination, but it greatly reduces sudden link failures. This approach is most suitable for high-mobility scenarios, like vehicles on a highway or users moving quickly, where blockages are intermittent and rapid response is needed. RIS deployment can virtually eliminate blind spots by providing alternate paths. However, the cost of deploying and managing many RIS units must be considered. This approach is more preferred in scenarios where the environment is rich in obstacles but changes relatively slowly. Non-diffractive beams method is a creative physical layer solution that gives the signal itself a way to detour around obstacles. These specialized beams are naturally robust to small or partial obstructions and are best suited for indoor or short-range situations. Overall, no single solution is perfect for all cases. In the future, terahertz communication systems will likely adopt a hybrid approach, combining multiple strategies to complement each other. Finally, we would like to share an experimental demonstration of the bending beam-based solutions. We built a proof-of-concept 140 GHz terahertz link using a programmable metasurface to realize the smart detour concept. In this setup, the transmitter produces a non-diffractive beam that can steer around obstacles in the near field. The system employs QPSK modulation and achieves a data rate of 1.6 Gbps. During tests, even when an object was introduced to block the direct line of sight, the metasurface-guided beam was able to bend and maintain the connection. This prototype validates the potential of our near-field obstacle avoidance method for terahertz communication. Thank you very much for your attention.